Hello, welcome to lesson 10.2, Coulomb's law, and this is really just going through many of the examples dealing with specifically this formula, F is equal to K Q1 Q2 over R squared, where F is the force, the electrostatic force between things measured in newtons. K is Coulomb's constant. Okay, Q1 and Q2 are the charges, and R is the distance between the charges, and specifically between the centers. All right, this formula can be found right here on the data sheet. Right, just right underneath electricity and magnetism, and Coulomb's constant can be found right here. It's a little off the screen, and I'm see if I can't zoom so that we can no, can't seem to find to make that work. So back to example number 1 here. We've got a positive charge of 4.0 times 10 to the negative 10 coulombs, exerting a force on a negative charge of 7 times 10 to the negative 10 coulombs, and the distance between the charges is 4 centimeters. We want to know the magnitude and nature of the charges between each other. So this is, we're going to just start with our formula. Okay, as we plug in the numbers, this is mostly just plugging in the numbers. However, dealing with all of these exponents and negative exponents, etc., can be a little bit difficult. And so I do encourage you just to type along just so that you can verify. This 4 centimeters, remember standard units for distance is meters, so that would be 0.04. And plugging that all into our calculator, we should wind up with a 1.6 times 10 to the negative 6 newtons. Now I know I put a negative here, and we didn't wind up with a negative answer here. The negative and positive is really difficult. The negative means really that they're just opposite charges and therefore is an attractive force. And so I'm going to just talk about that negative as being attractive, because like charges repel, meaning if you got positive or negative, and that will get you a positive result. It means a repulsive force. If you wind up with a negative value for force, you've got charges that are opposite of one another, and therefore it will be an attractive force. Okay, I would like you to try this next one. Pause the video, give this a try, and see how you do. Okay, just taking a look, we're going to start off with our formula and doing a manipulation. Multiplying both sides by r squared, dividing both sides by the force, leaving you here. Plugging in our numbers, r squared winds up being 0.0857, which after you square root both sides, right, the step here is to square root both sides, you're going to wind up with r is equal to 0.29 meters or 29 centimeters. This third one, what we're looking for is the net force acting upon the ball. And here we've got a positive 2.9 times 10 to the negative 7 newtons, and a negative force here, which means it is an attractive force this way caused by Q1. And we see the same sort of attractive force happening between Q2 and Q3 on the middle ball. However, they are both attractive forces, but going in opposite directions. And so as we deal with this, remembering that force is in fact a vector quantity, that these two forces, even though they are attractive forces, are actually going in opposite directions, which means we're going to just call this one negative and this one positive. They are both attractive forces. They'll calculate to negative, but normally the positive negative, remember, indicates direction. So as we type this in with our kq1, q2 over r squared, where we've been given charge 1, charge 2, distance, k is a constant, always the same, this force winds up being 0.02607 newtons. We're going to do the exact same thing on the other side. Again, we've got, let's change the color here, 1q, 2q, r squared for this one. Notice we do have one of the charges being the same, that middle ball, and this force winds up being 0.09178 newtons. So if we take the first force plus the second force to get the total force, what we need to remember is that we're calling this one negative, 0.02607, and we're going to add to this one that we've declared positive in the positive direction to the right, and so that gets you 0.066 newtons. Positive, which means it's to the right because we declared right to be positive. Now, the next question just asks, well, what if this charge, this Q1, is actually changed from negative to positive? Well, in that case, we would see this as being a repulsive force, right? And so this force would actually be going this way, and this force would be going this way. They'd both be going to the right. So, because of that, we're taking F1 plus F2 equals the total force, but in this case here, it's positive 0.02607 plus positive 0.09178 for a total of 0.12 newtons. And again, it's to the right, but notice because that is a repulsive force acting from Q1, we wind up with an answer that is much larger than what we had. In fact, it's almost twice as large. Changing the color here. Taking a look at number 5, this is number 5 here. Here we're now dealing where we're not given a whole lot of numbers. We've got KQQ over R squared, that should be a Q. And we're told what the force is. But we've got this new force, which uses one of the charges double. So instead of Q1, we'll go 2Q. The second one stays the same, so we'll put another Q in there. And the distance between the centers triples, 3R, all squared. Now, because of this square, that new force is going to get you K2QQ over 9R squared. And if we notice what's happening is we've got this 2/9 that's actually multiplied by the old force. So really what's happening here is we're taking 2/9 of the 2.5 times 10 to the negative 2, and that results in 5.6 times 10 to the negative 3 newtons. Okay, the direction of the force, again, we don't know because we haven't been given direction. We just know that the magnitude is going to be 2/9 of the original. So give this next one a try. Again, pause the video, give it a try, and then let's see how you did. Okay, the answer you should have gotten would have been 4 times the original amount, and that is because starting with our original, we're halving the distance. And halving the distance means we're going to see a stronger force. As we square everything with the distance, we find that it is 1/4 over 1/4 r squared, and this quarter, this fourth, comes back up to the numerator position just because it's kind of like we're dividing by a division. Okay, our last example now brings us into vectors. We do know that forces act in a directional motion. And so here we've been given this -2.1. So we've got a charge here, -2.1 times 10 to the -6, or microcoulombs. And it is sitting 2 centimeters west of this object B, 1.5 microcoulomb charge. Okay, because this is negative and this is positive, we will see this as being an attractive force. Okay, and so next we've got what object C sits below, south of, and this is the 1.8 microcoulomb, and it's sitting south of the object B, 3 centimeters. And so it is a repulsive force. So the net force acting upon this will be west, caused by A, and north, caused by C. Mark those as A, B, and C. Right, and so what we're going to do is we're going to find these two forces, call this force C, call this one force A, and it's going to make a new triangle that we're going to need to put together. When we take a look at force A, and we're just plugging in our numbers, and the numbers here, remembering this is also same as 0.02 meters, and the microcoulombs is actually times 10 to the -6, you should wind up with force A as being 70.8 newtons west. Now we'll actually keep our calculator with the 70.796 yada yada yada, but 70.8 just for purposes of writing this down. Force C, which is the one that's head north, and I think I've mixed those up here. Object B is here. This force was actually force caused by C heading north. This was force A, the one going west. Force C, again, we're using the KQ1 Q2 over R squared. Force C, when you put it all together, gets you 26.97 yada yada yada, or we'll just go 27.0 newtons, and that one is heading north. We need to put these two together, and so if we see force C going north at 27.0, and then basically from A we're going 70.8, this is our new triangle, so it's the new force is kind of coming up like this. Right, the new force or total force from them, and so that's to find the magnitude. We're using C squared is equal to A squared plus B squared. results in 75.8 newtons. The direction, based on the way that I've drawn this, the angle that we're going to get is west of north. Tan theta is equal to opposite over adjacent. And when you find that angle, you should wind up with 69 degrees west of north. Now that could also be 21 degrees north of west if you had reversed the order that you were putting those in. So that's it for the examples. If you've got any questions, please let me know, and thanks for watching.